Good morning, all. Welcome to the Advanced Air Traffic Services sessions. We are a little bit late as the previous session has been running late. We will try to get things on time, and even if we are a little bit late, that's nothing that's going to change. So today we have, here in this session, we have two talks. The first one is on volcanic SO2 height swim service, and it's going to be presented by Hugues Brenon, who works for BIRA as a research scientist. He's got expertise in remote sensing from satellite-based, airborne, and ground-based instruments to determine the concentration and distribution of some trace gases and aerosols in the Earth's atmosphere. He has experience in geodynamics with the implementation of geological models of telluric planets during his postgraduate degree in internal geophysics and geodynamics, and he's got a PhD in geophysics, the fellowship from the French government, about GNSS meteorology. So he's got in his profile, you will see he's got a whole list of different projects he worked on, and we met at some other projects and on which we worked together. So without further ado, I'll give you the Hugues Brenon and volcanic SO2 height swim service.
Thank you, Tanya. So good morning, everyone. So it's a pleasure for me to present you this work about the volcanic SO2 height. So I hope it's all right and you can see it properly on your screen. So this work took place last year in the frame of an engaged KTN catalyst funding that allow us to develop this kind of works. So you can see the idea is to look at the SO2 height, so the sulfur dioxide emitted from volcano, and to develop an early warning system. Early warnings that, I don't know, it's slow. Can you? Okay. So the partner of this catalyst project are Nicolas Tess and myself from the Royal Belgium Institute for Space Aeronomy. It's a collaboration with Scott Wilson from Eurocontrol. And also we had on board Rory Clarkson from Rolls-Royce as a consultant. So we use 3 satellite sensors, so TROPOMI, YASI on METOP A and YASI on METOP B, to detect and observe the sulfur dioxide and the height. And the idea is to transfer this as a swim service, transfer this information to the stakeholder. So the acronym of OPAS, it's Operational Alert Product for ATM via SWIM. For this study, it's also a collaboration with international partner. So you have the people I mentioned for OPAS, but there is also Leven Claris from the Free University of Brussels, who provide the data for YASI. Also American colleague from the SIMS and NOAA, who provide information from other sensors to make some validation of what we develop, and also partner from the University of Padova, Italian partner, and also the INGV Volcanic Observatory, and also UK partner and German partner. Here is the outline of my presentation. I will show you the motivation and the objective, then present the early warnings of volcanic SO2 height. Then we'll follow the Registry of OPAS SWIM service and future development. As you all remember, in 2010, the volcanic eruption of Eyjafjallajökull was quite dramatic for all the air traffic. I will not mention all this number, but you remember more than 100 flights was canceled and with a lot of financial loss. If we look at the scene in the Pacific Ocean, this shows you the frequent and occasional ash and sulfur producing eruption, where we could find for different routes some contamination from volcanic cloud. This is really a good motivation for us, and also to focus on the sulfur dioxide, because we can see that on this panel, there is some sulfidation mechanism that can appear in the engine. You can see, for example, on the right, depending on the temperature, there is a sulfidation of the first type with molten crystal mineral that can make some problem in the engine. Then there is also some sulfide diffusion process with other crystal mineral. This is a type 2. There is also a mix of these two types that makes the type 3. And we can see for lower temperatures, there is also the type 4 called corrosion fatigue. And there is also chlorine ion that take place. So all this sequence of contamination exposure can be a real problem for the maintenance of the, it requires really a maintenance of the engine, and that's a huge damage and cost for the aircraft manufacturer and also the airlines that have a contract with them. So that's a really good motivation. So the idea is to create a swim yellow service, yellow profile service called OPAS, with the aim of providing early warning of volcanic SO2 height. So we use 3 satellite sensors. You can see on the right panel, this is to show you what is the limit of detection of the SO2 mass from different sensors. You can see in yellow bullets all the broadband imager, for example, MODIS, and SEVERI for geostationary satellite, that can provide you really relevant information. But you can see that in terms of detection of sulfur dioxide, this is quite limited. On the other hand, there is a hyperspectral sensor, the blue bullet in infrared for Earth and YASI, where we can see that the pixel size, the pixel area is maybe less good than for the broadband imager, but you can have a better detection limit. And finally, if we look at the UV-Vis hyperspectral sensor and the one TROPOMI, we can see that the SO2 mass detection limit is under 0.1 teragram per kilometer square, which is really the best instrument actually to observe and quantify the SO2 emitted in the atmosphere. So we have YASI SO2 height and TROPOMI SO2 height on board this project. As an example, the best instrument before to observe the sulfur dioxide was OMI. You can see an example of Etna eruption, and you can see the difference between the two instruments. TROPOMI provide very good observation of the sulfur dioxide. This is really a nice improvement that has been achieved since TROPOMI is in the space or in the satellite orbiting around the Earth since 2017. So we want to provide a new alert, SO2 height, with also flight level contamination, and this contribute to an existing early warning system that had been developed in the frame of SACS, UNADIX AV project. UNADIX project is a Horizon 2020 project that took place from 2016 to 2019. During 3 years, 21 partners from 12 country in Europe, including Med Service, has collaborated to combine and harmonize data from satellite, Earth observation, and ground-based and airborne platform. The idea was to develop a prototype multi-hazard monitoring and early warning system, integrate the state-of-the-art of data assimilation and analysis system, and then to produce information available for the stakeholder through existing channel. So the idea at this time was to use SWIM, but because the procedure was not ready, we could not achieve that in the frame of UNADIX project. The focus of UNADIX project is a natural airborne hazard from dust, smoke, and volcano, also nuclear clouds. But this is quite confidential and not publicly available. And this is my institution, so the Royal Belgian Institute for Space Aeronomy was in charge of this early warning system. So we can take on board all this development in the frame of OPAS Engage project. And we managed during this project to develop operational calculation of SO2 height from tropome. You can take a look for more detail to the paper submitted. Basically, this is an iterative fitting procedure that to retrieve in the same time SO2 height and SO2 column. And the idea is to match observation of spectral radiancy with simulation. And for that, we use lookup table to have a fast access to simulation. We have also a convergence criteria. We use synthetic validation, so simulation of spectra with simulated noise for different height of sulfur dioxide at 2.5, 6.5, and 13.5 kilometer. You can see that over 25 Dobson units, so this is the unit to quantify the column of sulfur dioxide, we can see that over this threshold of 25 Dobson unit, we have a very good success with our algorithm. If we look at the interest of our algorithm, this is really fast with accuracy of 1 to 2 kilometers. We also develop some quality flag. However, we can see that under 25 Dobson units, we do not have success with our algorithm. Also, if there is high ash loading that can degrade our retrieval with underestimation of the sulfur dioxide height. We also have the algorithm of YASI that we use. This is also very fast with good results already demonstrated by Liv and Clarisse in 2014. However, we obtain a result between 5 and 18 kilometers with low performance for heavily saturated plume. Let's take a look to the eruption with the huge ash cloud from Raikoki volcano in June 2019. That was the most important eruption affecting long-line air traffic in the Pacific since Sarychev in 2009, with a gigantic amount of sulfur dioxide with a mass loading of 1.5 teragram and high up to 15 kilometers. You can see on the right panel the image from Sentinel-1 and also from ISS Astronaut, very impressive image. You can see the retrieval from YASI and tropome. Just at the start of the eruption, we can see that there is a good agreement between the two instruments. However, if we look at the source, what you can see in blue for YASI is a bit underestimated, and this is the effect, the saturation that I mentioned. But mainly when that's not close to the source with high concentration, the retrieval of YASI is really good, especially because you can obtain SO2 height for really low concentration. The early warnings that we develop, basically we send email notification. This is an example for the eruption Japanese volcano Nishinoshima in July 2020. We also provide links to observation images with relevant information, link also to Google Earth images. And in the same time, we provide also a link to data and tailored product. In this harmonized file in the netcdf format, you can have information of the SO2 column, SO2 height, SO2 contamination of the flight level. This is an example of contamination of flight level 150. Also level of severity and mass loading. That is really interesting for modeler who want to assimilate or consider this data in dispersion modeling. During this event, the flight GL5T flew in direction of Anchorage, the 4th of June 2019. According to the volcanic ash advisory, this plane could fly at an altitude of 14 kilometers for flight level 470. However, if we look at the observation from Tropomi and the contamination of flight level 470, we can see that there is strong contamination. Thanks to the observation of SO2 height, we can have this information. Here is the trajectory of the flight. So you can see that it's through the SO2 and ash cloud. And on the bottom right panel, you can see the trajectory of the flight. The blue cross show you the height of the plume. And you can see in the blue line, this is the SO2 column. So basically during 1 hour, the plane flew to important and huge concentration of SO2 column. This is why we develop OPAS SWIM service, and we are nearly, that means at the end of this month, this will be totally online. This is actually in the draft and nearly online for in the swim, but you can see what it looks like. So basically, this yellow profile notification service follows a definition and it is in line with the ATM information reference model. The protocol of this notification service is a subscription by email, and then people can get a notification of SO2 alert with information of SO2 height. And this is a simple protocol using internet IP, so the IP, and if you provide that, you can get access to the database of the warnings of SO2 height. You can simply contact me in this email address if you are interested. About the future development, so we have seen basically we want to develop some application API for the user, and you can see that this recent eruption of Lewotolo volcano took place. You can see that it could be great to have this kind of internet interface available for user, and that's we want to develop in the coming year. You can see that there is, looking at YASI observations, there is some warnings at the flight level 130, but also flight level 250 and 500 on the 29th and the 30th of November. If we look at a volcanic ash advisory, we can see that also information and restriction of flight level 500 was observed, but we can see that the flight level 250 was not really described. And this is really interested to combine forecast with near real-time warning in the future. We want also to use a complementary use of geostationary satellite and polar orbiting sensor. You can see on the left and the right the SO2I developed in OPAS, and in the middle you can see observation of ash RGB composite from Imawari provided by EUMETSAT. With a really high temporal resolution, these geostationary satellites are really interesting, but with a limited detection, and we want to combine both information from hyperspectral sensor with this kind of instrument. And the idea will be to continue this work in the frame of alarm project that just started last month. But I really encourage you to take a look to our website, and you can see that there already nice information available. And yeah, I hope you can find more information about what we will develop in the next 2 years. Basically, that's to develop more early warning system for space weather, environmental hotspots, also severe weather from nearby airports, and the continuity of OPAS with volcano, and also add dust and smoke early warnings. Thank you for your attention.
Thank you, Luc. Very, very interesting presentation. I guess while we are waiting for questions from the audience, I have a couple for you. So when you say near real time, what does it mean?
Okay, so basically near real time, when we speak about satellite data, there is a time delivery for ground-based station to get access to the data, and there is some treatment that need to be done, but basically that can be between 15 to 2 or 3 hours. So this is what we call near real time.
Okay, so but it's still, yeah, I guess it's and you have it then on every 15 or whatever couple of hours that
Yes.
you have it, and you have it constantly. It's not like with the forecast that you have it and then it's for next 6 hours. It's the same.
Yeah, so when I show you the volcanic ash advisory from the VAC, so they use observation, but then they provide forecasts that can be up to 6 to 12 hours. So we can see that there is really a good complementary use of combining the forecast and also a near real-time warning that we plan to make available with application for user, for the stakeholder.
Okay, good. And then do you already have the users of this product in aviation? Because I know it has been online for a few years. Do you know if there's anybody who really uses it in aviation, and what did you get their opinions on that?
So at the moment, well, the key user are the Volcanic Ash Advisory Center. This is a really nice control tool for them to have a near real-time monitoring platform when they can have a really selective detection of volcanic emission. We also have the aircraft manufacturers are really interested, I think, to Rolls-Royce or Safran, for example. This is really relevant for them to avoid the airline company to flew through the SO2 cloud, because there is a strong contamination and maintenance cost for that. And that's really interesting also for the pilot before their flight. And we already have a really nice feedback from the pilots. From the other aspect, this is also the responsibility for the National Weather Service, who are decided if the airspace can be open, for example, for other airborne hazards like dust or smoke. And the space weather aspect is less well known, but this is a really a strong disturbance of communication, and also the radiation are not good if you fly through a magnetic storm. So, and also the severe weather aspect, but this is something that is well, actually a lot of work have been done, but there is still progress that we can do for around the airport for really small convection that can take place. And the environmental hotspots, this is really important to fly and to avoid pollution and to, yeah, in the atmosphere, try to decrease this pollution. And yeah, so the idea is to combine with all this rerouting, and that's what we want to achieve in the alarm project.
Okay, well, thank you very much. I don't see any open questions from the audience so far. Let me check if there's anything in the chat. Okay, well, nothing there. So thank you very much, Hugh, for the presentation. We'll catch up later, I think.
Have a good
and
day.
Now,
take care.
yes, okay. And now we turn to Christiana Schmidt, who comes to us from Linköping University. She's a senior lecturer, and she holds a diploma in mathematics for finance and industry, a PhD in computer science from Braunschweig University of Technology in Germany, and she's been a docent from Linköping University, Sweden. After working as a postdoctoral research at State University of New York at Stony Brook, USA, and the Hebrew University of Jerusalem in Israel, she joined the Academic Excellence in ATM and UTM research group at Linköping University in Sweden in 2015. She became a senior lecturer in spring 2020, and her research interests include algorithms, computational geometry, mathematical optimization, and their application to transportation research, and in particular to ATM research. So, Christiana, could you please go ahead? I think you have a video, right?
I have a video, but your turn, yeah. Okay.
Okay, perfect, thank you.
There's no sound whoever is sharing.
Just we'll wait a second until they sort out.
About how to achieve CDOs for all aircraft, automated separation in TMAs, enabling flexible entry times and accounting for wake turbulence categories, which is joint work together with Tatiana and Valentin Polishuk, Ausa S., Javier Prats, Henrik Hardell, and Lucy Smetanova. So what's the background to our work? Well, we all know that air traffic volumes have increased over the last decades, and despite the current COVID situation, it is expected to grow again in the future. And while that comes with many benefits, it also comes with a high environmental impact and dramatically increased complexity for controllers. And those appear particularly in TMAs because there all the traffic converges. So what our overall goal is, it's to optimize arrival and departure procedures to alleviate both environmental impact and controller workload. And to alleviate the environmental impact, continuous descent operation are identified as a promising solution, for example, by Eurocontrol. So let's look at those CDOs in detail. The CDOs are optimized to the aircraft's operating capability, which means if we have aircraft with different characteristics, we also have different optimized trajectories. On the other hand, the STARs, so the strategically published arrival routes, they are done without taking the operating capability of each aircraft into account, so they severely limit the option of actually performing the optimum descent trajectories. Also, if we have different optimum trajectories, that reduces the vertical and temporal predictability of the incoming traffic, which directly increases the controller workload, and that means the controller will react by increasing separation buffers, for example, by using altitude assignments, speed adjustments, path stretching. And all of these will result in losses in airspace and runway capacity, which we, of course, do not want in highly congested TMAs. Also, the technique the controller applies degrade the performance of the descent operation, so we lose several of those nice environmental benefits that CDO entail. Also, the crew does not know the duration of the open loop vector instruction and when the aircraft will rejoin the initial route. That means that the FMS cannot predict the remaining distance to go and also not optimize the trajectory. So all these together result in that in today's busy TMAs, CDOs are hardly used. And we think one important point there to circumnavigate that is to support controllers in the separation task using automation tools. So how have we done so far to go to that way? Well, in work prior to what I'm telling you today, we optimized, we presented an optimization framework for aircraft arrival routes, where we guarantee temporal separation. So any pair of consecutive aircraft was temporarily separated, but we used a uniform value. So always the same temporal separation. We used realistic CDO speed profiles, and we assumed that the arrival time to the TMA entry point is fixed for each aircraft. When we applied this framework to Stockholm TMA with an average traffic intensity scenario, we could accommodate only about 78% of the flights with CDOs. So why is that? It's not because of some computational limit of our optimization framework or the solvers that we use, it's because of the input. Aircraft arrive to the TMA entry points with less temporal separation than those 2 minutes. So that directly makes the problem infeasible, and we had to filter them out. Of course, what we could have done is to allow non-optimal speed profiles, and then we also would lose several of those nice CDO benefits. So we'll suggest to do something else today. We assume that the speed profiles along the en route segments can be adapted. So the aircraft arrival time falls in a time window, and within this time window, we can pick a time. That is, our profiles give both an RTA at the TMA entry point and a route length in the TMA. And when we use that, we could achieve a high throughput. So when we apply this to Stockholm TMA to one of the busiest hours of operation in 2018, we could enable all aircraft to fly CDOs. And we present another improvement. We let the separation be determined by the category of the leading and the trailing aircraft. And of course, that may change over time. We have merging traffic, so what was before the leading aircraft will change over time for any aircraft. Okay, so let's look at the concept of operation that we suggest to support the framework that we present. We assume that aircraft arrive to an extended TMA, and then they follow published routes to those yellow TMA entry points. In that time, they are still in the en route phase, and the FMS will compute the earliest and latest possible time of arrival at those yellow TMA entry points. And that depends, for example, on the aircraft performance and so on. And then we don't have any stars published, but we have a finite set of possible routes from these entry points. And the controller will request from each aircraft one profile per route length and per discrete values of RTAs in this interval between earliest and latest possible arrival time at the TMA entry point. When the controller receives them, the automated ground system will compute an optimal arrival tree and assign RTAs. So we have one arrival route per entry point of the metering fix. All aircraft follow the same route from that. And it's optimized for a specific time interval, so it will change during the day. It also means that we assign a new type of descent. So what we want is that when the aircraft arrive at the TMA entry point, they know the RTA and they know the arrival tree. This is computationally expensive. So It could also mean that we want to establish the communication between the aircraft and the controller well before the extended TMA to allow for those computations. So let's look at the components of our actual framework. We have two main components. One is the computation of CDO speed profiles for different lengths of the entry point runway path for all aircraft that arrive in the considered time interval. And the second is the computation of the arrival trees that allow for temporal separation. All aircraft fly along the arrival path, all use CDO speed profiles, and our temporal separation depends on the category of the leading and trailing aircraft. To compute these arrival trees, we use mixed integer programming, and in particular, we use a discretization. We overlay our TMA with a square grid, and then each vertex has directed edges to its 8 neighbors, like the pink one on the right-hand side. And these directed edges are the building blocks of our arrival trees. What that means is that we have a discrete set of possible entry point runway path lengths. So for each possible discrete path length and each aircraft, we compute a CDO speed profile. So we'll compute one, and then this is the input to our MIP. And this is the optimization of the vertical profile for a given route length. So let's look at the grid-based MIP formulation. In the previous MIP model, we had computed arrival trees, aircraft following specific speed profiles. We guaranteed temporal separation of a uniform value. We assumed that the arrival time to entry points is fixed, and we had several operational requirements. We said that no more than 2 routes may merge at any point, because merging could create a point of complexity, and having more routes merge increases it. And then for all practical purposes, we don't want to have them arbitrarily close to each other. That would still mean an area of high complexity, so we want to have them separated. Aircraft dynamics mean that we cannot have arbitrarily sharp terms, so we have an angle threshold and combine that with a minimum edge length, because otherwise, even if you have large angles, you can on a small area make a sharp turn, which again would be practically infeasible. We are able to avoid obstacles like no-fly zones, and we make a smooth transition between consecutive trees of consecutive time periods so they don't differ too much. And today we add the flexibility of times of arrival at the TMA entry points and the separation criteria based on the wake turbulence categories. So one variable that's kind of important, which we use to encode everything, I thought to introduce it to it. It's a binary variable, YAJPNT. It indicates whether aircraft A, using speed profile P, occupied the nth vertex on the path from its entry point, J, at time T. But I'm not going to go into more math. So one new constraint is a flexible time of arrival at the TMA. So instead of requiring that aircraft A arrives at entry point B at fixed time TBA, it now arrives within an interval, and we add those constraints to enforce that it arrives exactly once, it doesn't arrive at any other time, and we pick one profile. And then the other new constraint is a separation with different weight turbulence categories. So before, as I said, we had this uniform value, all consecutive aircraft pairs were separated by sigma. Now we want to take the ICAO's aircraft categories, light, medium, heavy, and we could also use super into account. Sigma AB is now the temporal separation if the leading aircraft belongs to category A and the trailing aircraft belongs to category B. And what we'll do is we'll define C1 as heavy and medium and C2 as light. And then we introduce 2 classes of constraints, one if those 2 aircraft are of different categories and one if they are of the same category. Okay, let's look at the generation of CDO profiles. So we compute descent trajectories for each arriving aircraft, each possible route length within the TMA, and we assume usual CDOs for all descents, so either thrust and no speed breaks. Our route lengths give a fixed distance to go, so we can formulate the optimization of the vertical profile as an optimal control problem. And we assume a few things. We assume no wind and international standard atmospheric conditions, and we integrate the aircraft model, the current altitude, the true airspeed at the top of descent, and the distance to go. So let's look at 2 examples for that. Here we have for distance to go 36, 66, and 102 nautical miles, Airbus A320, a medium aircraft, and an Embraer EMB Phenom 100, a light aircraft. What we can observe is that if we look at the same distance to go, the light aircraft has a lower airspeed than the medium aircraft, which means it will take longer for the light aircraft to fly each segment in the TMA. Okay, and with that, let's look at the experimental study. We consider again Stockholm TMA. We look at one of the busiest hours of operation in 2018, May 16 from 5 to 6 a.m. We use historical flight trajectories from OpenSky and aircraft performance parameters from Beta 4.1. And if our aircraft model is not in Beta, then we use a comparable aircraft with respect to performance and dimensions. We solve our MIP with Gurobi. We split the hour that we consider in 2 times 30 minutes. Why? Well, because of 2 aircraft, we needed to stretch a path. And when they then at some point already arrived at the runway and we still use a stretched path, this is no longer optimal. So we need to compute a new tree regularly, somehow in the order of the lengths that the aircraft spend in the TMA. And then we use those constraints that enforce consistency so that the trees do not differ too much. And we use an 11 by 15 grid, so we have a merge point separation of about 6 nautical miles. We use a chaos separation minima, so if the leading aircraft is heavy medium and the trailing is light, then we have 3 minutes, and in all other combination 2 minutes. We schedule all aircraft to arrive within plus minus 5 minutes of the planned arrival time, the original arrival time, so we have a time window of 10 minutes. The given flights in our 11 by 15 grids have path lengths of 30 nautical miles to 108 nautical miles, so those are 14 discrete possible path lengths, and we compute 14 trajectories per aircraft, all the way at the same time at the TMA entry point. In the first experiment, we just use this original traffic. So at the left, you can see the resulting trees. The white is for the first half hour, and the yellow are the changes to those routes from entry point 1 and 2 to that tree. And on the right-hand side, you can see for all aircraft, the timing when it goes at the entry points, at the different merge point, and at the runway. So we can schedule all of that. All the 30 aircraft, all fly CDO, it's feasible. And what we get is an average entry time deviation of 2.27 minutes. So from this original plan time. And let's look a bit at how that moves. So we have here the different merge points and the bottom, the runway, where you can see with which intervals they arrive. And the average time separation at the runway are 2.14 minutes. We look at a different experiment where we change the fleet mix and increase the number of light aircraft. So this is more proof of concept to see how different aircraft categories influence our trees. For that, we artificially increase the share of light aircraft to 20%. And that's far off from what we can observe in reality. So what we did is we just randomly chose 6 aircraft and substituted them by a light aircraft. Again, remember, they usually have slower speed profiles for arrivals. So what that meant here is that we could only accommodate 25 of the 30 aircraft. The trees are actually the same. And here we have the timing. So now the average entry time deviation is lower, 2.03 minutes, but simply because we have fewer aircraft that we schedule. And again, let's look at least only the runway, where you see that before every of those randomly integrated turquoise light aircraft, we have 3 minutes separation at least at the runway, and we can also make sure that the optimization framework ensures that it will be overall, and we also check that. Okay, let's evaluate what we did. First, we look at some KPIs proposed by Eurocontrol EC. The first one is the minimum time to final. So the time to final is the time from an aircraft's current position to the final approach point. And the minimum time to final that we computed as the minimum time needed from any point within a grid cell to the final approach using any of the trajectories passing the cell. Should I try sharing something, or can you make the video work again?
Let's see what they which team says. Think should we try to get Christiana to share, or?
Minutes. So from this original plan time, and let's look a bit at how that moves. So we have here the different merge points and the runway, where you can see which interval they arrive, and the average time separation at the runway are 2.14 minutes. We look at a different experiment where we change the fleet mix and increase the number of flight aircraft. So this is more proof of concept to see how different aircraft categories influence our trees. For that, we artificially increase the share of light aircraft to 20%. That's far off from what we can observe in reality. So we just randomly chose 6 aircraft and substituted them by light aircraft. And somehow I still hear you. Remember, I tried to simply share a video. Have slower speed profiles for riders. So what that meant here is that we could only accommodate. Can you turn off the sound? The aircraft, the two are actually the same. And here we have the time.
How about you try with the Christiana? No.
This one is the minimum time to final. So the time to final is the time from an aircraft's current position to the final approach point. And the minimum time to final we computed as the minimum time needed from any point within a grid cell to the final approach using any of the trajectories passing the cell. And what you have here from left to right are the original trajectories, the minimum time to final, the optimized trajectories, and the minimum time to final. And what we can observe is first that we have reduced lateral dispersion simply because all our aircraft follow the predefined routes. And we can also observe a significant reduction in the average time spent in TMA. It's 9.5 minutes versus 15.1 minutes for the actual trajectories. Second criteria is spacing deviation. A spacing for a pair of arriving aircraft is a difference in time to final. So the spacing deviation is defined for a pair of leading and trailing aircraft at time t. And this will give us information on the control error. So again, left is actual trajectories, right are the optimized ones. Here we cannot observe a significant reduction, but the idea is that the implementation will reduce the controller workload because they are no longer responsible for vectoring, but only have to monitor the progress of the aircraft along the predefined routes and do minor corrections in case of some problems. Finally, as one of those KPIs, let's look at the sequence pressure. So the sequence pressure for an aircraft at time t is the number of aircraft with the same time to final in a given time window, and we use 2 minutes. This reflects the aircraft density, and we calculated for each aircraft when it's present in the TMA in discrete time steps. And again, at the left, we have that for the actual trajectories, and at the right for the optimized ones. And here we can see a significant reduction in the sequence pressure for our optimized routes. Okay, finally, let's look also at the vertical efficiency and the distance flown in TMA. So here, actual routes in blue, optimized CDO-enabled routes in orange. We have altitude over distance to go in TMA. For the actual routes, we can see that they reach lower altitudes earlier, and they have long periods of level flight, and some at very low altitudes that will inadvertently lead to extra fuel burn and high levels of noise. And finally, let's look at distance in TMA, same color coding. One note here, that's an approximation because we use for each edge a length of 6 nautical miles, while the axis parallel edges are shorter than 6 nautical miles and the diagonal ones are longer than 6 nautical miles. If we use that, then we get a total distance covered in the TMA of 1,958 nautical miles for the actual routes and 1,578 nautical miles for the optimized CDO-enabled routes. And that's a reduction more, the difference is more than how we could underestimate. So we get an improvement. So let's look at conclusion and outlook. We showed that enabling flexible arrival times allows us to schedule all flights with CDOs. We guarantee temporal separation, which is based on the aircraft categories. This contributes to reduced environmental impact and an automated ground support for controllers. Our routes improve the vertical efficiency and the distance and average time in TMA. And we also proposed a concept of operation that can support our framework. For future work, we like to also evaluate the noise impact, the lateral efficiency. We like to look at a trade-off between robustness and uncertainty, and the influence of the time window when we shrink that or make it larger. How will that affect our ability to schedule? And with that, I say thank you so much for your attention, and I look forward to your questions.
Okay.
Thank you. Thank you, Christiana. So I think we have plenty of questions. Some you answered already, but I think for others, it could be a good thing to maybe go. I'll start with this like from the open question. There is a Felix that asks, are there any plans to incorporate the wind in the trajectory generation? This could be a considerable factor along 100 nautical miles.
Yeah, so that thing is that we'll have to integrate that in the optimization, and we would probably have to, the plan is to start with using at least an approximation to the wind, because when we optimize, so we take the length of the profile as an input to the optimization, but that could be any profile of that length, which means we also have to give the direction of the different edges when we want to have the wind direction as well. And there the problem is if we actually take the complete wind for all possible edge directions, then that will blow up the complete computational framework of the mixed integer programming so much that this will most likely not be computationally feasible. So the goal is to find an approximation where we integrate wind, at least for a certain subset of the edge directions, always putting them together or something like that, to have wind integrated, but not to integrate it completely per edge direction, as then our IP will kind of blow up. So that's the plan, to continue with integrating wind there.
Okay, then we have another question from Konstantinos from IFACEA. Does your study take into consideration the potential congestion of AF due to the fact that 40 nautical miles around terminal area are excluded from environmental KPIs per performance regulation?
No, we don't take any congestion into account, at least, but there's not something that for certain TMA is here. I'm also not completely sure in what way you would want us to take that into account. So if you have a follow-up on that, I'd be happy to answer that.
Okay, so Konstantinos, if you could then type it up in what you meant, then we will get there. I have from my side, I have one thing. So far, this is just this is the optimization that you're working on. It's not something that you didn't test it in the real life. It's just simulations, right?
Yeah. It's just. I mean, I said that we use the historical data, so we really just computed for the aircraft that arrived at that point in time, we generated the CDO profiles for the different lengths in the TMA and then optimized rows based on that. So, or the arrival trees that take that if they arrive at that point in time, and those are the aircraft that actually arrived, then we can have the temporal separation on the routes where they fly CDOs completely to the runway.
Sorry, I think there was also a nice question from Felix you already answered in the by text. That he was asking about trajectory calculation for CDO paths. For the different path lengths between 30 and 100 nautical miles, the descent angle varies to eat up the necessary altitude, or do you insert deviations to elongate the real flown path to avoid excessively steep descents? What speed differences are due to the different descent angles?
Let me try to share the slides again. There was one picture that I had. Here on the lower right, you can see that we have the trajectories with a different type of descent depending on what the actual time of arrival to the entry point to the yellow is. So yes, we have different angles, so they are not starting the top of descent at the same point in time, and that means you get the actual flown path there. So this is this picture in the lower right I'm trying to insert here, where we have the latest and the earliest possible trajectory.
We have another question from Sonar that asks, if you change top of descent, how it is far from AIP?
How is far from AIP?
I guess AIP airport information, like from the I guess the published procedures.
Yeah, but what does it mean? How is far from?
What I don't know in which way. How is it far? So I guess how different it is.
Well, again, what the idea is that we don't use any kind of published routes. We will optimize arrival routes in each time step to the traffic that actually arrives to enable all aircraft to fly CDOs. So this is something that is not integrated currently. So yes, we do change the top of descent to allow that, but it's not the optimization of the arrival tree with respect to the actual current traffic. That's essentially the difference. Where we have the automation tool that allows you to have those trees to determine which kind of profiles the actual aircraft should use, and also to enable that all of them will fly CDOs. And that is something that will support the controller as well, because if they fly according to these routes, then we have the temporal separation included. So they don't have to provide the vectoring as a controller, but only support if there are any deviations from what was planned. So that's the difference.
I guess that then also if the CDO becomes more, let's say, more used, then some of the procedures should be published taking CDO into account.
Yeah, but you cannot really publish them because, again, it will always depend on the aircraft in which order and of which type they will arrive at the different entry points, and also how many. So if you have way fewer aircraft in a specific time interval, then of course the trees will be shorter, because then you don't have to stretch a bit to include the temporal separation of aircraft from different paths that arrive. So there's, in the end, there's a discrete set of routes, but there's still a large number of routes, which I don't think makes sense to publish at that point.
And let's close with the last couple of questions. Sebastian says, in open procedures, what pilots need for CDOs is an accurate DTG provided to them and updated continuously. Will ATCOS be able to provide that with this concept?
Yep. I mean, so at the point in time when they have the information, they have the complete information. And that's the plan to have that when they actually enter.
And then there's another question from somebody else. Says, how do you generate separation between aircraft all the way throughout the descent and not only at specific points with RTAs?
Well, because we keep track, as I said, the our variables keep track of if an aircraft is at what the number of vortex, what is the vortex, at what point in time is it there, and with which speed profile. And then we can look at any possible time interval and kind of count how many aircraft can pass within a certain time interval and see what the leading and trailing was. And with that, we can see that the temporal separation is kept at any point on the routes that we look at. So we don't really use the RTAs for that. We use our variables that track. The RTAs are essentially the output from the optimization, because we pick the actual speed profile, the length of the route with the optimization, and that results in an RTA for the aircraft. So it's not the actual input.
Okay, well, thank you very much, Christiana, and thank you very much, Hugues.
Try to continue a bit. Yeah.
Yeah, well, we sorted it out without too much wasted time, and we started 8 minutes late, and we finished 8 minutes late, so I guess we are right on time. Well, thank you also all for typing up so many interesting questions, and I'm sure Christiana will take her time also to answer them. And see you in the virtual room. Thank you very much. Bye-bye.
Right.
Hello, my name is Carl Weston, and I'm a postdoctor at Linköping University in Sweden. On behalf of my co-authors, Tiago Nunes, Stefano Bonelli, and Clark Borst, I invite you to a live webinar on the poster titled Balancing Transparency and Conformance of an AI Conflict Detection and Resolution Support System. The webinar is held on November 8th in the poster session between 1:30 and 2 p.m. The poster presents ongoing work within the SESAR exploratory research on the research project Mahalo. Mahalo asks a simple but important question. Should we design automation that is strategic conformal, that is adapts to the individual, or should we design automation that is transparent and explains itself to the human? Do we actually need both? In Mahalo, we will explore the impact of these on controller trust and acceptance of an AI conflict detection and resolution system. Visit our poster exhibition page and join our live webinar to find out more. Thank you. Hello, my name is Carl Weston, and I'm a postdoctor at Linköping University in Sweden. On behalf of my co-authors, Tiago Nunes, Stefano Bonelli, and Clark Borst, I invite you to a live webinar on the poster titled Balancing Transparency and Conformance of an AI Conflict Detection and Resolution Support System. The webinar is held on November 8th in the poster session between 1:30 and 2 p.m. The poster presents ongoing work within the SESAR exploratory research on the research project Mahalo. Mahalo asks a simple but important question. Should we design automation that is strategic conformal, that is adapts to the individual, or should we design automation that is transparent and explains itself to the human? Do we actually need both? In Mahalo, we will explore the impact of these on controller trust and acceptance of an AI conflict detection and resolution system. Visit our poster exhibition page and join our live webinar to find out more. Thank you.